So when looking at the normal distribution curve, this can standardize every absolute value and can then in the following be used to quantify those that are as extreme at least as that STAT score. And if that is quantified, where we know? If that is quantified for differences between a sample mean and a population mean, yes. Yes, I'm recording. Thank you. Thanks for the reminder. I appreciate it. And for the comparison, we talked about random samples. We talked about drawing random samples from a population. And you end up with a sample that has a certain mean and has a certain variability. So this sample will be to some extent reflecting the population mean. Depending on the size, it will vary in terms of the variability of that estimate and in the accuracy and precision of that estimate. That means if you have a very large sample, the mean that you're getting from that sample will likely be a fairly accurate estimate of the population mean. In addition to that, if you draw repeated samples, and we know that from the calculation of the standard error of the mean, which is the variability of these randomly drawn samples and the mean estimates deriving from each of those samples. In addition to that, if the sample size is larger, all these samples will be a more accurate representation and estimate of the population mean, and the variability of these samples will be less. And remember the calculation of the standard error of the mean, that's the population standard deviation divided by the square root of the sample size. So this is our first parametric test that we will be conducting. That's a so-called STAT test. So we are comparing in this test the sample mean to the population mean. So we're estimating the population mean and we're seeing where does this sample that I have drawn locate itself in reference to the population mean. And what in essence you want to do, and we talked about this already briefly, we're standardizing these differences between the sample mean and the population mean and estimating the variability of these differences. So we're calculating the sample mean minus the population mean divided by the standard error of the mean. And that was the formula which we looked at in chapter 6, where we basically have also seen that this STAT score, this is the sample mean minus the population mean divided by the standard error of the mean. So we have a variability in our sample mean estimates. This is the relationship between the sample as an individual score, the normal distribution deriving from individual scores, and the distribution of the individual score mean estimates. And this is this relationship that we had labeled as the so-called central limit theorem. So if we have individual scores, we get a normal distribution, which is presenting with a wider variability as compared to the derived distribution of the means, which is a variability and the spread of mean estimates derived from hypothetically randomly drawn mean estimates, so randomly drawn samples. So we are relating the variability of the individual of the samples with the individual scores to the variability of these sample mean estimates in order to be able to estimate the population mean from which the sample was drawn. And this relationship is quantified here by calculation of the set. So basically the comparison distribution here is the distribution of the sample means and the differences of these distribution of the sample means to the actual population mean. So we have here means, which is we usually would have, and this will prompt you to think of that in the use case. You have a sample given, you have a mean of a sample, you have a population mean given, and you will compare the sample mean and the population mean by estimating this difference, which is here the numerator, and the denominator of the standard error of the mean. This will prompt you to think of a STAT test. is the standard error of the mean with a given standard deviation from the population. So in the question, you will recognize that the SAT test is indicated by basically looking at the standard deviation, whether it has been calculated and estimated based on the sample standard deviation or from the population. In case it is given as a population standard deviation, think of a SAT test. And we will talk about what this means today when we dig deep into hypothesis testing. And next, I want to speak about that example slide, the PDF file. So these are these extra slides that I have posted with module 9. So basically, remember, hypothesis testing as a basis foundation, as a basic approach, means to amalgamate the quantification and the estimation of the difference between the sample and the population mean by basically creating a binary insight, whether it is significantly different or not. And significantly different means basically that there's a statistically significant difference. And this is quantified with a probability of the null hypothesis being correct or not. And if that null hypothesis is correct at a probability level of less than 5% in most cases, we will reject the null hypothesis as being false. And then we accept the alternative hypothesis that the difference is significantly different. So again, the defendant is considered not guilty until the guilt is proven. So this is the null hypothesis. So we're basically assuming that the sample mean and the population mean is not significantly different under the null hypothesis. And the prosecutor tries to prove the guilt. So you basically, this is what you're testing. We're testing against the null hypothesis. And the alternative hypothesis is true if the probability of this null hypothesis being true is smaller than 5%. So that would constitute enough evidence to reject the null hypothesis. So it's important in this context to also review type 1 and type 2 error. And this table really nicely outlines that. So if we have a null hypothesis that is true, and the sample mean and the population mean are indeed not different, we are making a right decision if we're accepting the null hypothesis and acquit our defendant. If we have a null hypothesis that is true, and it's really it's truly not guilty, and we're rejecting the null hypothesis, then we're making a wrong decision. And then we're rejecting something that we shouldn't have rejected. That's a so-called type 1 error, as we have discussed. If we have a null hypothesis that is false, and the H1 or alternative hypothesis is actually true, and we are not rejecting, but we're accepting the null hypothesis, we're basically making a wrong decision, and we're committing a so-called type 2 error. If we're rejecting the null hypothesis and the research hypothesis is indeed true, we're making the right decision. So this is a concept that's super important to keep in mind. And today we're going to go through the calculation steps to actually quantify that. So just to illustrate, and this is in the PDF, just to illustrate, there's like this, these two pictures that basically, so you're basically assuming a false positive by rejecting something that you shouldn't have rejected, and you're basically accepting something that should have been rejected, and you're accepting this as being correct. So that's a false negative. So, and now when you think of hypothesis testing, essentially you have now a sample mean, and you're estimating the standard error of the mean. So you're estimating the distribution of these means of hypothetically randomly drawn samples. So this gives you a distribution of these sample mean estimates. And you want to characterize this. You assume these are normally distributed, and you're standardizing them as per the standard error of the mean. And the standard error of the mean in the context of hypothesis testing basically becomes your standardization tool of this distribution of the sample means. So you're stratifying and you're standardizing your distribution of the sample means according to standard errors of the mean. And then based on this distribution of the sample means, you can basically determine these extreme values beyond which you're basically deriving a p-value that sums on both sides up to 5%. So you have 2.5% on the left side and 2.5% on the right side. And you can see this to be true when you look at the set-score table, when you look at minus 1.96, which is commonly the threshold for a normal distribution, which basically gives you a 5% p-value as the type 1 error rate that is acceptable on both sides of the normal distribution curve of the sample distribution of the means. So 2.5% at minus 1.96 and at plus 1.96, you essentially get you get 0.975, which is 100 minus 2.5. So that gets you to 97.5. So that's the upper end. That's the tail to the right. And these two in sum up to 5%. And these 5% essentially are the so-called alpha level. That is your acceptable type 1 error rate. So this is what you're willing to accept. You can also set this not at 5%, you can also set this as 10%. And when you set it at 10%, you're willing to accept more risk of being wrong, to reject something that should not be rejected, which is the definition of a type 1 error. So you're extending that probability you're willing to make a mistake. Yes.
So this table shows me the p-value?
Yes. So the percentage that we have used for the population is, so you remember the law of large numbers, right? If you have 10% of prevalence in a population and you draw one individual, you have a 10% chance that this individual is, I don't know, diabetic or whatsoever. Same applies here. So these percentages in the distribution of the sample means, and that's a very good question in this context, because it translates directly here in probabilities. So these percentages are to be interpreted as probabilities. So you get a difference with the set score. You get a difference between a sample mean and a population mean, and you're standardizing this distribution of the sample means, or the sample mean differences, according to the standard error of the mean, which constitutes the variability from that sample that you have at hand based on the standard deviation of the population. Under the assumption that if you draw a small sample, you will have more variability because it could be from different parts of the population. If it's a large sample, it will be more likely representing the entire population with less estimate and more likely reflecting the population mean quite accurately. Also, if you have a larger standard deviation from the population and you have a wider range of potential values and you have a wider distribution, your sample, your considerably small sample in relationship to the population, may more likely have extreme values and more variability represented as well. So this is that relationship between the standard error of the mean, the standard deviation, and the sample size. So now you're characterizing and you're standardizing your distribution of the sample means and the derived differences between the sample mean at hand from your one sample to the population mean, and you standardize that was your standard error of the mean. And the resultant set score translates then in a probability of this being significantly different, as per definition, statistically significantly different from the population mean, or not. Make sense? Any questions? Yes.
So this is not.
This is a set score, yes, but it's not a typical. It's not the same set score as, for example, the standardization of a population, where you have a certain proportion of the population contained. Now we're translating this, and with the central limit theorem, we are translating this into set scores of a distribution of the sample means, and translating this in a probability of our sample being significantly different from the population mean.
Like how?
By calculating this formula, right? Yep.
You're looking at, I thought you have to look above a certain amount.
As extreme, yes.
Yeah.
Yep. Good question. It's hypothetically it can be a maximum of 100%. This is an identical sample and population mean. Then it would be 100% the resultant, which is a rarity to find, which is virtually impossible to find in a real life scenario. So the further away it is, the larger this numerator is going to be, the more variability you have because of a smaller sample size, for example, or a larger variability in your population, the larger this value is going to become, and the smaller that set is going to become. Yeah, because it's in the denominator, and the smaller set will indicate a higher probability.
So you were to ask us to do values.
Yeah.
You wouldn't give us, well, you would have to give us something above a certain deviation, right? But you would, like, what would be something you would ask?
A question that hypothetically could be on a quiz could be something like this. Oops, what's this? Could be one of these examples here, which I have put. Well, you see the practice quizzes, right? The question could be something like that, and we will do this. So you're conducting a set test of 50 people, Werber square of the SATs. So you have from your sample of 50 people, you have 542, and you're comparing this to a population mean of 500 with a standard deviation of 100. The trick, the most important thing, if I just may chime in for that, the most important thing is that you recognize what is given. And that's when I talk about you need to extract this information from the question. What was your question? Yeah. Yeah, we will do that. Yes, that's why lab day is for, that's what the rev is for. So that's the plan. So right now I'm just really focusing on the concept, because the concept is important, because it's distinctly different from other concepts that will come your way later on.
Oh, and
yeah.
In terms of the probability, that, like in tables, where would we need to use that?
Where would you what?
Where would we need to use those?
Well, this probability, it could be, and you will see the example that we will do in a second, which we will walk through. This probability needs to be quantified, and it could be a question that you have to read out a certain probability, that you have to find out a certain p-value, which is less likely. It's usually not done, because there are easier ways to do that. But what you will certainly do is like quantifying confidence intervals, and this is where the loop closes between hypothesis testing and the confidence interval. That's today's lecture, once we get to that. So when going back now, so we have now any other questions? Things will get clearer as we do it, trust me on that. So it's right now it's conceptual, and I understand it's quite a learning curve. I'm well aware. But if you go through the concepts and you see them then in practice with the examples, it will become clearer. So if we accept the 5% p-value as our alpha, which is the acceptable type 1 error rate, we have 1.96 and minus 1.96. If we are willing to accept 10%, for example, which is done in some rare use cases, you will need to find the corresponding value with 5%, which is to be found here between 1.65 and 1.64. So it is considered to be 1.65. So this is when you are willing to accept a 10% probability of rejecting something you shouldn't have rejected.
Always 10%? Always 10%?
1.65 is always 10%, yeah. So the principle, the application principle remains the same if you use it for the distribution of the sample means or for the population and the quantification of proportions of the population. Any questions? Yes.
Going to 1.65, there is a one that says 50.
Can you repeat the question, please?
Why are we doing 1.65 and not 1.6?
Well, it's 1.6 is here, that's 0.055. So 1.65 is 0.0495, which is closer to 5%. And 5% for a two-sided test would be on both sides of the distribution curve. So you can also do 1%, for example. This is where you have to go even further. And this is located somewhere here at 2.58. This is where you find an alpha of 1%. So in the context of something felt really hard, in the context of big data, for example, in my world, where we have like 100,000 of patients, you will need to be a little bit more stringent on your alpha, because of the large sample size, everything will become significant. So we are sometimes defining lower alphas, just for the sake of being more on erring on the lower end. So, but let's go back to the, no, we want to the slides. So here there's extra slides, and there is an example that I want to present to you. So again, we are now, this is the distribution of the sample means, and we are testing whether this distribution of the sample means, whether the population means is outside of our actual extremes that we're willing to accept, and whether it actually is significantly different. And this p-value deriving from the set scores here is actually smaller than our alpha. So that is the idea of hypothesis testing with a set score. And so we have 6 steps. So here only 5 steps, but we basically have 5 steps that we're using in hypothesis testing. Nolan Heinzen defines an additional step to that, which is basically describing the distributions. So, but let's stick with these 5 steps now for the purpose of these slides. But please make sure that you know, because some of the questions, actually, let's quickly do that. Just to not be sloppy about it, make sure that these have been discussed. So in 6 steps of hypothesis testing, you first identify the populations. So you know what is the population, you know what is the sample. You define the distribution, so you're comparing the distribution of the sample means to your actual population mean. The assumptions of a parametric test is random sample, normal distribution, and independent data points for all. Then choose the appropriate hypothesis test. So if you have the population mean, the population standard deviation, and you're comparing a sample mean to these 2 parameters, you essentially will use a set test. And we will do more testing, and you will need to know how to identify the appropriate test. Step 2, you're stating null and research hypothesis. Remember, sample mean versus population mean. You have a null hypothesis would be that the sample mean and the population mean are identical. Whereas the alternative hypothesis would imply that sample mean and population mean are not identical. The symbolic notation we're going to do in the example. Then we determine the characteristics of the comparison distribution. That is essentially where we are quantifying, we're taking the standard deviation, we're quantifying the sample size, and we're calculating the standard error of the mean. Next, we determine the critical values, and the critical values, that's our 1.96, minus 1.96 and plus 1.96, which gets us to our alpha. So once we have determined our alpha, then we find the critical values, then we find the numerical cutoffs, and then we're indicating the points beyond which we would reject the null hypothesis. Fifth, we're calculating the test statistic, and this is nothing else but this formula. This is basically quantifying exactly this set, which is the sample mean minus the population mean divided by the standard error of the mean gets us a set. Based on this test statistic, we're lastly making a decision. If the set is exceeding our critical thresholds on this distribution, then we're rejecting. If it doesn't, we're accepting the null hypothesis. If the set that we're calculating from the set statistic is exceeding our critical threshold, we are rejecting the null hypothesis. If it's within our critical thresholds, we're accepting it. So now we want to do an example. And our example here is now, is the blood pressure of smoking males no, actually it's cholesterol. Is the total cholesterol of smoking males is a typo? It's wrongly stated. Is the total cholesterol of smoking males the same as in the general population of the US? Yes.
If it's outside of the threshold, it rejects the law.
Correct, because then our sample is further away from our population mean. You got to think of it in the difference, because you really numerically you're standardizing the difference, because the population mean doesn't change irrespective of your distribution. So you're characterizing and standardizing your sample distribution mean, but you essentially you're really standardizing your difference. Exactly, and then the null hypothesis is to be accepted. But if you're rejecting the null hypothesis, you say, oh, yeah, got it? Okay, good. Okay, so we are now comparing sample that we have drawn, which is a sample of smoking male US citizens, and we're comparing this to the cholesterol of the US population. So we have here a population cholesterol. I don't know who is familiar with cholesterol values. You assume something, total cholesterol somewhere in the realm of 200 milligrams per deciliter to be normal. Everything exceeding that is considered slightly hypercholesterolemic, so was exceeded higher cholesterol. So we're comparing now the total cholesterol of smoking males to that group, to the population. So first, and I don't want to go towards one-sided alternatives for now. Okay, let's do two-sided. We're doing two-sided tests. That means we're taking the alpha and we're distributing it to both sides. That means we have two tails that we have to pay attention to. It's 2.5% on the right side, 2.5% on the left side. The null hypothesis here is that mu, our sample mean, is identical to the population mean. Mu equals mu0. It should be m rather than mu0, but it is sample mean versus population mean. And the alternative hypothesis that is different between the sample mean is different from the population mean. So mu, sample mean, is equal to 211 milligrams per deciliter. So 1 deciliter is 100 milliliters. So don't get sidetracked by that. And here the sample mean is unequal to 200 milligrams per deciliter. So the sample mean is different from the population mean. I will only briefly talk about this. We will do this on next class in practice. So in the simplest approach, we will actually talk about it today. In the simplest approach, you assume the two tails to be our alpha. This is true if you do a so-called two-sided test, which is the most commonly used test. So you will always assume these two tails to be our alpha. In some certain circumstances, which are rather a rarity, I haven't seen many in the course of my research career, to be honest, and it's rather hard to kind of get this through a statistical review when you send this somewhere as a paper. But in some rare instances, you will have a situation where it actually makes sense to define a one-sided hypothesis. And that would imply that your null hypothesis actually points in a certain direction, which says like the sample mean is smaller equal to my population mean. And the research hypothesis actually says that the sample mean is greater than the population mean. When would this be the case? When you will with certainty assume that it only will change, that it always has to change in one direction only. An example one could think of, and which is an example you actually have in some of the questions, is, for example, toddlers or children. They are growing, they're not shrinking. So when you have a direction that is just the normal direction things evolve, then you will assume this to go in one direction for the null hypothesis. Only if it doesn't go there, then you reject the null hypothesis. But let's for now let this be. So one side that is really hypothesis-driven kind of question. It really needs to be justified by the underlying research question. So this is a definition of the alpha. So the alpha is the type 1 error rate. So this is rejecting the null hypothesis when the null hypothesis is actually true. Is actually your false positive rate. Then we go towards calculation of the set statistic. And that is x bar, or the sample mean, m, minus the population mean, mu0, or mu, divided by sigma divided by square root of the n, which we know is the standard error. So that's a one sample set test. So now in the end of the day, what you want to do, you want to quantify that p-value that has more extreme values than your critical value, your cutoff value. So this becomes your p-value. And this needs to be calculated. So this p-value will be calculated from your set, and you need to know how to read that from the distribution table. And this is what we will be doing today. So based on that set score and the p-value, you will then accept or reject the null hypothesis. And this is now the example. So we have cholesterol. We know from the population that the cholesterol for the entire population is 211 milligrams per deciliter. The standard deviation sigma is 46 milligrams per deciliter. So we are now testing this against an alpha. So we do a two-sided test, and we're accepting an alpha of 5%. Again, there's another.
Is this a different example?
No, it's the same example. It was just before, it was wrongly. I think I mentioned it. It is cholesterol. Yeah, my bad. Sorry for that. Yep, it's cholesterol. But the principle is the same in a way. So, okay, so now assume that we have a random sample of 25 hypertensive male smokers. That this is where the blood pressure comes in, because they have hypertension in addition to that. Okay, so we, and the average cholesterol is X. So this X bar, or this M, is 195, and for the second group, it's 227. So now we want to calculate this for our first sample that is has a cholesterol of 195. And this is the example, and this is just a nice example because it nicely outlines in conjunction with an actual graphical depiction of the sample distribution of the mean. It shows basically that distribution. So we are calculating our first set by mean, sample mean, minus population mean, which is 195 minus 211. And we're dividing it by sigma, which is 46, divided by square root of the n of 25, which is 5. So it's basically 16 divided by 46 divided by 5. So it's 16 divided by 9 point something. And that gets us to a set of minus 1.74. Yes, please.
Where is the 46 gone?
That's the standard deviation of our sample. This was here. That's the 46. For good observation, thanks. So we have 195 minus 211 divided by 46 divided by the square root of the n of 25. Gets us a set score of minus 1.74. If we go now in the distribution table, we have minus 1.74. This is 0.0409, so 0.41.
We're using this table when you have negative numbers to get the p-value.
So because it's two-sided, it will only be everything to the left of that number. So if you have a negative set score, this will be everything to the left will be characterized with that P. If you have a positive number, you have two possibilities. Either you read it from the negative set score because it's the same, it's symmetrically, or you go to the positive one and you go to 1.74, which is this one, and you calculate 1 minus 0.9591. Gets you the same. It's again the 0.0441. So now we have 0.041 because it's a two-sided test, and this is where the catch is. That's for a two-sided test the catch. Because it's two-sided, you have to consider this 0.041 for both sides. And that's where it's getting tricky. Because you need to multiply now your 4% with 2, and your resultant is 8.2%. And this 8.2% are exceeding our alpha. That means we are not rejecting the null hypothesis. So this is a very nice graphical depiction of how to essentially quantify this set scores, the alpha, bring the set score in conjunction with the alpha and make a decision based on that. And the trick is that you need to multiply this P by 2 because you need to consider both sides.
So you're rejecting it, you're not.
You're not rejecting it. You're accepting the null hypothesis because
it's higher than
5.
Yeah.
That's the problem. Because the probability of your null hypothesis being correct is higher than not being correct.
Tell you that it's not significant.
If it were smaller than 5%, then you would consider it to be significantly different. Correct. But if it's greater than 5%, you assume the probability of the null hypothesis being true greater than it not being true. Yeah. I know this is a little tricky, and because you kind of you are rejecting something that actually inherently would consider yeah, so you need to think a little bit around. Okay, so this is two-sided. What is now the case for the second sample, which had a cholesterol, mean cholesterol of 227? So if you look at the calculation here, you had 195 minus 211. That gives you minus 16. If you're using 227 instead of 195, you have plus 16. So the resultant set score is going to be plus 1.74, and your calculation is going to be identical to this calculation, because now you're basically assuming you're starting with the greater tail, and you still have to multiply it by 2 to account for both tails. Both alphas, or both type 1 error rates. So 227 and 195, same result, absolutely identical, just a positive set score as the resultant. So now we talked briefly about a one-sided test. So we are not rejecting here. We are rejecting now. So it's important that these 95% are essentially not saying that the null hypothesis is true, but it gives you an interval and it gives you a probability of it likely being true, but it doesn't give you certainty. So it's all about probabilities. There's no certainty in statistics. It's all revolves around probabilities. If you have a one-sided test and your null hypothesis would be that the mu, so your sample mean, is actually greater than your mean cholesterol in the US population, your calculation would be identical. But since it's one-sided test, you do not multiply it by 2, but you're only assuming that alpha and that tail that points in the direction in which your research hypothesis is pointing. So it's pointing to the lower end. So you only assume this 0.041. On the opposite end, if you have a null hypothesis where you basically say that the sample mean is smaller equal to the cholesterol in the population, And your research hypothesis points towards the sample mean being greater than this 211. Your research hypothesis basically fills now everything above your calculated SAT score. And that basically becomes now that p-value of your hypothesis test. So this being said, with example 1, here you are rejecting the null hypothesis. With example 2, here you're not rejecting it. Any questions on hypothesis testing in that context of the example? What's important to keep in mind, it's not only about that p-value, it's not only about this probability of the null hypothesis or the alternative hypothesis being true, it is also about the actual difference. So if you're comparing a sample mean to a population mean, and this is significantly different with a very large sample size, that does not necessarily mean that you're really looking at a significant, relevant, meaningful difference. And this is the distinction that Nolan and Heinz make, is statistically significant does not necessarily mean it's an important finding. Just because it's significant, that does not necessarily mean it's really useful. Particularly with large numbers, big data, you find everything to be significant. Doesn't necessarily really provide you much insight. So there's a distinction between statistically significant and important, clinically meaningful. So please keep that in mind, particularly nowadays with really large sample sizes in many analyses. We live in times where data is just collected for everything, so sample sizes have increased, data volume has increased. Please make sure you are aware between this distinction. One-tailed and two-tailed tests, we've talked about this. So critical values are always determined by the acceptable alpha, so it's 1.96 for 2.5% on both sides, adding up to 5% for both sides. You make a decision if your critical value is exceeded by your calculated test statistic. The problem nowadays is that with an increase of the use of advanced statistical methods, advanced statistical software, you can test a lot of things very, very simply. And that essentially allowed for two problems to arise. So one is harking, and the other one is p-hacking. Harking means that you hypothesize after your research results are known. Essentially, that means that you explore your data and you subset your data and you look at certain subsets of your data based on what you find to be true. So you see a signal in only looking for diabetics, you will subset and only look at diabetics. So it creates a problem on its own right if you only look at smaller subsets. And it's basically like massaging the data until you actually found something that is significant based on the results that you have obtained. And then you phrase your hypothesis around what you have found. And then you have a hypothesis and becomes a self-fulfilling prophecy to basically have done a significant difference. It's not that uncommon, unfortunately. P-hacking is basically the same thing. You are hacking your data in smaller chunks until you find subgroups that are somewhat significantly different from each other, also frowned upon to do that. You should have, as we have learned, you should pre-register and be transparent about your research hypothesis and research questions, and you should follow a very rigorously defined and designed analytic plan when you do your analysis. Good, so that was hypothesis testing. I don't think it's particularly complicated, but it's employing the principle will be a little tricky. But I want to build on that right away with the next lecture with confidence intervals, because there's a very logically consequence. That's a very logically following thought process. So we have hypothesis testing, and hypothesis testing, basically we're creating a dichotomous insight. So we're saying this is significantly different, and that's what it is. It's different, and then we assume this to be statistically significant different. What it doesn't pay attention to is the actual the difference between two populations, or between the sample and the population. And secondly, it doesn't pay attention to the variability that you find in the samples. And the example here that Nolan and Heinzen give are the work from Haidt, Fenema, and Lerman, who investigated the gender differences between males and females. So they found, so there were, just as backpedaling and kind of giving an insight, so in the 70s, 80s, there were analysis done that basically favored one gender over another in terms of their capabilities to solve mathematical problems. As we know, these are marginal differences, which are, it's not really reasonable to assume that there are real differences. So what they found in their meta-analysis, that you had really small differences when it came to actual differences, because what they found was an almost perfect overlap between these two populations of males and females. The only thing that was different, and this is the problem that I wanted to outline, the only thing that was different were the means. In these studies, there were differences between the means, but overall, the normal distribution was a perfect overlay. So you may have some extremes that may be different to some extent, but overall, the bulk of the data and the majority of people are comparable between the genders. The only thing they found, they acknowledged, were that there were some proneness to be better at one task over another. So, for example, females were better with computational problems and males were better with problem solving. So that remains to be evaluated. But essentially, the overall distribution was comparable, and the difference is marginal and more statistical in nature. And this emphasizes the importance to pay attention to variability and the distribution as a whole, rather than just resorting on hypothesis testing only. And this is what Nolan and Heinzen label as the so-called new statistics. And the new statistics want to go beyond relying only on p-values being smaller than the critical value, the alpha. They basically also involve effect sizes, confidence intervals, and the computation of meta-analysis. We will talk about this today briefly. Meta-analysis is a very elegant tool to actually summarize findings from several studies. So this is definitely a format, and you will nowadays definitely be asked to provide much more descriptive data for your research articles. You will be asked to show the distribution of your population, and there's much more interest in descriptive statistics nowadays, for good reason. Because when you do hypothesis testing, the only thing that you're really comparing are so-called point estimates. So a mean of a sample to estimate the population mean is a so-called point estimate. You have one point, you have one mean, and that one mean means to reflect the population mean. But what it really comes down to, and what is really important to quantify, to understand, is a so-called interval estimate. So if you want to estimate the population mean with your sample and the quantification of a sample mean, you essentially want to have an idea what is a range within which you realistically can estimate the population mean. And that's a so-called interval estimate. And in this context, we basically, the most commonly computed, most commonly reported interval estimate is the so-called confidence interval. So if you remember the probability lecture, that was chapter 5, sampling and probability, we talked about confidence. So the confidence is basically the personal subjective perception of an event to occur or not. So confidence is basically an interval estimate that gives you an interval within which you are, with a certain probability, confident that you contain, in the context of sample versus population mean, you are confident that your interval will contain that population mean. So for a sample, you essentially have then a range of data. You have a point estimates that define an interval within which you have a certain probability of confidence, or your confidence to a certain probability to kind of capture the population mean. And it's basically evolving around the mean. So you have the normal distribution of your sample, and you have two markers that are symmetrically around the mean, defining that area and bringing from a point estimate of that mean this to the next level to define an interval and the probability within that interval to capture the population mean. So how is that essentially done practically? So you have a normal curve. You need to quantify these bounds of the CI, and you determine and set statistics, and you convert those set statistics back into raw means. What does that mean? And let's start with the graphical depiction. So we have an alpha of 5%, which is the most commonly used alpha. If you are taking this alpha, you basically can say now you can invert these 5%, and you can say that if these tails are 5%, if the population mean is outside of these tails, I assume my sample to be significantly different from the population mean, from the population distribution. However, if my population mean is within bounds defining 2.5% on either side, I can assume the null hypothesis to be true. And this is where confidence intervals give you much additional information about variability. And secondly, they also allow you to hypothesis test your sample and population mean. So practically, this is done by okay, so this is lower and upper. So we have a lower bound of the confidence interval, and we have an upper bound of the confidence interval. So this is meant to be upper typo. So we have now lower would be the minus set, so that's minus 1.96 multiplied by the standard error of the mean, because that's how you come back to the raw score, plus the mean. And this is the same formula that we utilized to basically calculate from an individual set score back to the raw score, if you remember that. The only thing that's different now is we're using now values that define the critical values. So we're just calculating the raw score for the critical values at 5%. That's all we're doing. So this will allow for you to calculate the confidence interval. So M upper, so upper bound of the confidence interval, will basically then be plus 1.96 multiplied by the standard error of the mean plus the mean. And this gives you this bound. That's the confidence interval. And that's really as simple as this is. I don't want to go much into details now. We will carry on 30 minutes into effect size. I just want to quickly do a quick calculation. So if we take an example, let's take this example. Let's take 7.29. You're conducting a set test on a sample of 50 people. So my sample N is now 50. A university admission test in the US, we know the SAT, we have a population mean mu is 542. Oh no, 500. So we have a population mean of 500, a standard deviation sigma. I try to zoom in without losing this. Okay, so we have a population mean of 500, a standard deviation of 100. So our sigma is 100. Our sample mean is 542. So that's our X bar. So 542. And now we know that the calculation of our set is being done by calculating set is now M 542 minus our mu, which is 500, divided by, first the standard error of the mean. So now we have standard error of the mean is sigma divided by square root of the n. So this is our sigma. So our set is now m minus mu divided by our standard error of the mean. And that's a set of 2.96. So our set of 2.96 is now a p one-sided. 2.96 from the set score table. 2.96 on the set score table is basically 2.96 is this one. Is 0.9985. So 0.9985 is 1 minus 0.9985. So that's very small. Thank you for asking the question. 2.98, because you would need to read it from the negative, and I read it from the positive. So you get that with two way, so it was 2.97. So you either go to the negative and you read this value from here, which is 0.0015. So that's 0.15%. So 0.0015 and P2 sided. The other way around is you actually calculate, if you have a positive set score, you basically go to the positive and you calculate 1 minus that positive p-value. So P2 sided would then be this multiplied by 2. So our alpha is defined as 5%. So we see now that 0.03 will not exceed 5%. Thereby, our sample is significantly different from the population mean. Add a p-value, add an alpha of 5%. If I were to calculate now the 95% confidence interval, and I would like to calculate the lower bound and the upper bound, you would basically have the mean of my sample minus 1.96 multiplied by the standard error of the mean. That would be 514. And the upper bound is now my X bar plus 1.96 multiplied by my standard error of the mean, 569.
Did you do that 1.96?
Because that's my 5% on both sides. So this is a 95% CI. You can also make this 90% CI The 95 and the 90% CI would be 1.65 is equals mean minus 1.65 multiplied by the standard error of the mean. So that's 1.65 if you remember. So the same would be here is plus 1.65 multiplied by the standard error of the mean, 565. So it is a narrow range because you are actually less confident you're going to contain your standard error of the mean. If you go to 99%, you actually do this x bar minus 2.58, oops, 2.58 multiplied by the standard error of the mean. And this is now 542 plus 2.58 multiplied by the standard error of the mean. So these are actually your different levels of confidence. So you are within this interval, 95% confidence, 90% confidence, and 99% confidence to contain the population mean of 500. Make sense? Any question on this? This is as a concept, this is quite important. And I think it nicely ties together with the hypothesis testing. We basically have the same thresholds in a way. So, okay, so in 5 minutes, we can quickly also chat about effect sizes. So now if you standardize your sample distribution of the means with a standard error of the mean, keeping in mind, standard error of the mean is the standard deviation divided by the square root of the sample size. The problem you have with the standard error of the mean, this value, since you have the square root of the sample size in the denominator, the estimate of the standard error of the mean is strongly dependent on the sample size. So you don't want that essentially. So thereby, there is an alternative marker, which is essentially the so-called effect size. And this effect size is basically utilizing the standard deviation only instead of the standard error of the mean. So by that, it basically remains unaffected by the sample size, which strongly affects hypothesis testing. So you basically, you're calculating it with the formula here. You're calculating the so-called D, Cohen's D. So you calculate D as the difference between the sample mean and the population mean, dividing it by the standard deviation only. Please do not confuse standard error of the mean and sigma and distinguish between the actual set and the D. The reason why this is important, because if you have effect sizes, you want to really carve out the effect of those differences between the sample and the population mean. And if you have effects of sample size, you will get in a situation like that where you basically have here two different, you have the same means, but the significance will be on those with less variability. So variability plays a major role in hypothesis testing, and dividing it by the standard deviation rather than the standard error of the mean takes this out of the equation and focuses and puts the emphasis back on the difference. And Cohen's D is a way to do that. It will keep a focus on the difference rather than on the sample size. And this D has conventions which are being utilized to characterize these effect sizes into either small, medium, or large. So between 0.2 and 0.5, it's small. Between 0.5 and 0.8, it's medium. Greater than 0.8, it's large. And these effect sizes, not only the effect sizes, also the actual estimates are then in an additional step being summarized in what is called a meta-analysis. And a meta-analysis is basically utilizing the strength of an effect size that you can compare various studies, the effect size of various studies, independent of sample size, different sample sizes in each of those studies across all studies. A meta-analysis basically utilizes this comparability by amalgamating all the study results into one overarching analysis. So this is a so-called forest plot, which is kind of a standard way of depicting effect sizes in a meta-analysis, where basically you have each row corresponds with a respective study, and the value for the effect size is here shown with an estimate, a point estimate, and the interval estimate around this point estimate. You're using then quite advanced models to basically derive here an overall estimate of the effect size across all studies. Thereby, you really take full advantage of all individual studies, and a meta-analysis is considered the highest level of scientific evidence in the realm of science. So hypothetically, you go meta-analysis, randomized controlled trial, cohort study, case control study, and then you come to cross-sectional study. But meta-analysis are considered the highest piece of scientific evidence. That's all I have for today. There will be some more meta-analysis next time, but have a nice evening.
Yeah.
Thank you. Yes.